Blockchain scaling. Existing cryptocurrencies do not scale. So what does that mean? So what we often refer to as scale is the number of transactions. So this means the number of transactions that we can push through a network. But it could also mean like the volume in terms of US dollar or pound or Swiss franc. So there are really different types of scaling properties that we're looking after, right? So it's not always, we're not always looking for the number of TPS themselves. So on Bitcoin and Ethereum, we have about 10 transactions per second, maybe slightly more on Ethereum, but this is really, it's not that big of a change. It's not a magnitude, it's not an order of magnitude higher. And on Bitcoin, what matters is the size of a transaction in kilobytes, because there's no quasi-true incomplete language. So the bigger the size of a transaction, the more expensive it gets. And in Ethereum, it's the transaction complexity is measured in gas. That's the kind of complexity that you require to execute a transaction. Now, why don't blockchains scale? Why doesn't it scale? So on the one side, you have many users. I mean, many is a qualitative expression, but you can have, or you should ideally have like millions of users. And the other side, you have many validators, so certainly more than 10, maybe not a million, but it should also be a large number. And this is kind of a tension, right? You can't. It's tricky to inform all users about state changes that are conducted by all validators. So it's just a scaling problem in itself, right? It's just the information propagation itself to everyone does take time. If you look at the blockchain layers, so that's a possible representation, you have different limitations. So for example, on the CPU level, you have the signature verification, which can be a bottleneck. And there have been many works by the core developers of Bitcoin and Ethereum in order to speed up the signature verification, and this actually sped up the blockchain synchronization process. On the network layer, you have the latency, right, between the peers. You have their bandwidth. You have their tolerance to errors, packet losses, etc. Right? So there are several properties that you can improve on the network layer. On the blockchain layer, this is mostly the consensus complexity. So how fast or slow do nodes reach consensus? And on the application layer, it might be the overhead of an EVM, of a virtual machine or so. How can you build more efficient programs? So there are different, there are these, or you can have signature verification codes that might run faster or something, right? So there, on all these layers, you can actually improve the blockchain security if you like to. And the beautiful thing is, if you do improve on any of these layers, then these improvements compound into the other layers. Right? So all the other layers become better by together. So how can we now scale a blockchain? So basically on the previous slide, you can imagine we could scale by just increasing the internet speed. If the internet speed becomes like 100 times faster, latency is cut down by 10 times, tenfold, then the blockchains will have a much faster throughput already, which is not bad, right? So it's really a possible scaling possibility. So you can also try to tweak the consensus complexity. So the communication complexity of your consensus mechanism should ideally be small, so that you don't have to communicate with many peers in order to reach an agreement. You could also subdivide the problem into so-called shards, or partition the network into different clusters, and these clusters are smaller, so they will reach consensus faster individually, and you still have the problem of later somehow updating the global state once you need to make a payment or a transaction across shards. And fourth point, so the main focus of this today's lecture is the off-chain or the delayed on-chain settlement. So you perform some transactions off-chain and you settle them at a later point in time. So again, the beautiful thing is that all these improvements here, scaling improvements, are complementary, right? So an improvement on one layer will improve the other layers. So what does it mean to have an off-chain transaction? Well, it's basically a transaction that's outside the blockchain, but it's secured by the blockchain. So it's not a trustless transaction. It is a trustless transaction. It's not a transaction where you have to put trust in someone. Ideally, you shouldn't. Otherwise, most of the permissionless systems that we're discussing, they're really open and permissionless systems, and we don't require any third-party entity that we have to trust. So why is Offchain exciting? Well, because the underlying idea is that we have either 0 or 1 transactions to join an off-chain protocol, right? So this is here an initial joining step. For some protocols, we don't have to have any transaction to join the protocol. For some, we have to have this initiation transaction. That really depends on your off-chain protocol. And then afterwards, we have this channel or something set up where we can perform thousands of transactions securely off-chain, ideally. And they don't touch the blockchain, right? So only later on, when we settle with either 0 or 1 transactions, and we can leave the off-chain protocol. So here you have like at most one on-chain transaction to join, at most one on-chain transaction to leave. And this means you have done 2 on-chain transactions to perform thousands of off-chain transactions. That's the ideal setting. Now, what you would get out of this is that you don't have any consensus latencies if the monetary amount are fully on-chain and secured on-chain. And obviously you shouldn't pay the miners, right? You only need to pay the miners for this and this transaction, but not for those thousands of off-chain transactions. And ideally, we want to achieve all this while still having a non-custodial security. And I think the best feature of off-chain technology is that it's backward compatible. You can install it on a blockchain and you don't have to change anything on the underlying blockchain. Obviously, there are some limitations to this, depending on the features that you request or that you require for your off-chain design. But there is at least the capability of an off-chain solution for most blockchains. Now, I still want to throw in a cautionary note. Even though we might achieve non-custodial security, it's not necessarily the same security as an on-chain transaction, right? There are still some dangers that might appear, and it's not exactly the same security model. So don't think it's really just as secure as an on-chain transaction. Typically, it's not. So we have written an SOK with several co-authors here at TU Wien, TU Delft, King's College, and Imperial College in London. And this is basically a paper that summarizes all the off-chain technologies that are out there. And I invite you to go through this if you have time. So which off-chain solution should we look into? So in this lecture, we'll be looking in particular at channel networks and at commit chains. And we go through each of the properties individually.